Hi everybody and welcome to session 8 of Phil 2002, Logic, How to Defeat Your Foes with Reasoning. In the previous session I was introducing you to a new proof system. So the first proof system that we had in the course was the truth table system, and the truth table system really is a semantics for the language that doubles as a proof system. So you have your propositional logic, you translate, you interpret each of the parts of the propositional logic using the truth tables, and then once you've done that you can situate everything inside a truth table and actually carry out various proofs. One of the limitations of the truth table system is that truth tables can get very big and be very horrible. And once you make an error inside a truth table because of the size of the thing, that error can get carried forward through to the end, and it's very difficult to find the error and to actually come up with the right result in a reliable fashion. So what we do is we move to the truth tree system, which enables us to provide the same kinds of proofs as the truth table system, but without the attendant risk of error. So what we've got so far are some rules for the truth tree system. There are two types of rules. There are the rules for the actual process that we undergo, where you take propositions inside the language and you break them apart using the tree system. And then there are rules for when the tree is actually finished. And you've got a closure rule, which tells you to close any branch that has a proposition and its negation on it. And then you've got the completion rule, which says that the tree is completed either when every branch closes or when every proposition that can have a rule applied to it has had that rule applied to it. The basic modus operandi of the truth tree system is that we take a complex proposition and the truth tree system yells at us as soon as we write that down in our truth tree, this proposition is true, and we're trying to work out what else is true given the truth of that proposition, and we do that by applying the rules to break the proposition down to get to all of the possible situations that under which the proposition is true or false. Now what's interesting about the truth tree system, all of the possible situations under which the proposition is true. What's interesting about the truth tree system is that in a really important sense it represents the same kinds of possibilities that the truth table does. So remember, the truth table is a map of possibility space where every possibility is written out in detail. The truth tree system also represents possibilities. In particular, whenever you've got an open branch, that's representing a possibility of a certain kind. And we're going to see exactly how that works when we now, in this session, apply the truth tree system to some arguments. So just to remind you of the rules, here they are. When you've got alpha or beta, so when you've got a disjunction, that's a branching rule, and that splits into alpha on one side or beta on the other side. When you've got a biconditional, alpha, biconditional beta, that's also a branching rule. It splits. On one side, the two things, alpha and beta, are falling together or standing together. On the other side, they're standing together or falling together. It doesn't matter which order these go in. So as long as on one side you have alpha and beta being both negated, and on the other side you have alpha and beta being both unnegated, you don't have a problem. What you don't want is to mix these, where you say have alpha on one side and along with not beta, and on the other side not alpha along with beta. So we could, if we want, write the biconditional rule down as follows, and it would be exactly the same rule. We split, and on one side we have alpha, beta, on the other side we have not alpha, not beta. The order of these columns is not really important to the way that we do the truth trees. Next we have the conditional rule, alpha arrow beta. This is also a branching rule. On one side we have the failure of the thing on the left, so the first thing is false, and on the right hand side we have beta being true. We have the conjunction rule. The conjunction rule tells us that when alpha and beta are true together, then we have a column, and in the first part of the column we have alpha being true, and in the second part of the column we have beta being true. Then we have the first of our negated rules, and this rule here is the double negation. So when you've got not alpha, you can conclude alpha from that. And over here we've got the negated disjunction rule. The negated disjunction rule is a column rule. So when the disjunction is false, then both sides are false together. So when it's the case that not alpha or beta, then not alpha is true, and it's the case that not beta is true. Here we've got the negated biconditional. When the biconditional is false, then the alpha and the beta have different truth values on the two sides. So on one side you've got not alpha and beta, and on the other side you've got alpha and not beta. Over here we've got the negated conditional rule. When the conditional is false, you've got the first thing and you don't have the second thing. And so when the negated conditional is true, you have alpha and not beta in a column underneath the conditional. Next, we have the negated conjunction. The negated conjunction is true when either one side is false or the other side is false. So it's a branching rule, and on one side you have not alpha, on the other side you have not beta. Then we have the closure rule. The closure rule just tells us that a branch is closed when you've got a proposition and its negation, or a basic proposition and its negation. It's very important that you only apply the closure rule to basic propositions, right? So if you had a branch that had this on it, right, so you've got A and B, and then under that you've got not A and B. You wouldn't close the proposition even though you've got the proposition and its negation. What you would have to do is break it apart, because the closure rule only applies to basic propositions. So you'd start by breaking up the conjunction at the top to get A and B in a column underneath it, and then you would do the negated conjunction to get not A, not B. And now you can apply the closure rule because we've got basic propositions and the negations. So if you look at this left-hand branch, we've got the basic proposition A and its negation not A, so we close that. Over here we've got the basic proposition and its negation, basic proposition B and its negation not B, and so we close that, and that would be the application of the closure rule. Okay, next we have the completion rule, and the completion rule tells us that a tree is completed when either every branch is closed or when everything that can have a rule applied to it has had that rule applied to it. All right, what we're going to do now is we're going to apply the truth tree system to arguments. What we want to do is we want to use the truth tree rules to test for the validity of an argument. Here's the basic idea. An argument is valid when the truth tree for that argument, and I'll show you what a truth tree for an argument looks like in a moment, but an argument is valid when the truth tree for that argument is such that every branch on the truth tree closes, right? So we've put the argument inside the truth tree, we've done the entire truth tree. If every branch closes, then the argument is valid. An argument is invalid when the tree is complete and at least one branch on the truth tree for the argument remains open. We're going to have examples of what this looks like in a moment when I go through some particular cases, but it's useful to have the broad structure of what we're looking for in mind before we go ahead. So when an argument is valid, your truth tree is going to close on every branch, and when an argument's invalid, your truth tree is going to stay open on at least one branch. Now, we've got to be careful, because what it takes to situate an argument inside a truth tree is not simply a matter of writing down all of the premises and the conclusion and then doing the truth tree. We have to be a little bit careful about exactly what the structure of the tree is in order to get out the right result. So when I say that an argument is valid when every branch on the truth tree for that argument closes, I mean that in the particular way that we're going to situate truth trees inside, situate arguments inside truth trees in a moment. I don't mean just write down the argument and then do the truth tree. You have to do something else to the argument before you can actually test it. There's a difference between doing a truth tree on a bunch of propositions and testing those propositions for validity. All right, so with that in mind, how do we actually apply the truth tree method to an argument? Now, remember what the truth tree actually does. The truth tree only represents things that are true. It says everything in this truth tree is true, and what you do is you work out what else is true given the assumption that the things at the start of the tree are true. And you're always just trying to break it down into its sort of most basic constituents which are going to be true. Now, you can represent falsity in a sort of indirect way. You can't have something in the truth tree saying this is false merely in virtue of being in the truth tree. What you can do, however, is you can take a proposition, you can negate it, and you can put that in the truth tree. So when you're saying the negation of this proposition is true, that's just another way of saying that the proposition itself is false. Okay, so how do we actually test for validity with respect to an argument? So the test for validity is not just a matter of writing down all of the propositions and then doing the truth tree system. We actually have to do something a little bit different. What we have to do is we sort of assume that the premises of the argument are true and that the negation of the conclusion of the argument is also true. Now, to sort of take a step back to get a feel for what we're doing, we're actually using a very particular kind of proof method when we do this. This kind of proof method shows up in a range of other areas. It's a broad proof method inside philosophy, but you also use it inside mathematics. And the type of proof method that we're using is called reductio ad absurdum. So that's the Latin name for it. Reductio ad absurdum is sort of almost literally translated means to reduce to absurdity. And what you do is you take an argument that someone's given you and you show that that argument is a bad argument by showing that the argument leads to some kind of absurdity. What a reductio ad absurdum actually does is it takes an argument or take something that you want to prove, and you assume that that thing is false, and then you show that it leads to a contradiction, right? So reductio ad absurdum always assumes the thing that you're trying to prove is false, and then you try and demonstrate that a contradiction follows from that. Because then if a contradiction follows from that, then you can conclude that that initial assumption that the thing that you are trying to prove is false is actually incorrect, so you can then conclude that the thing you're trying to prove is in fact true. So here's an example. Suppose that you want to prove that there are infinitely many primes. So if we think about the natural numbers, which are the counting numbers, 1, 2, 3, 4, 5, 6, and so on. There's an infinite number of natural numbers, and there's also an infinite number of prime numbers, right? So here are some of the primes. How can you prove that there's an infinite number of prime numbers? Well, the proof, or one of the standard proofs for the claim that there's an infinite number of prime numbers, is a proof that goes by reductio ad absurdum. What you do is you assume that there's a finite number of primes, right? Pick a number. You could say, well, let's just suppose that there's 100 primes. And by assuming that, what you do is you suppose that there's 100 primes, only 100 primes, right? Which is to say that there's some finite number, and then you show that that leads to a contradiction, right? It leads to an absurd result. And in virtue of leading to an absurd result, you reject the claim that there's merely a finite number of primes, and that you get then to the result that there's an infinite number, right? So you assume the sort of finite thing, you show that that goes bad, and then you conclude to the infinite thing, right? And that's sort of what we're doing in the truth tree system. What we're going to do is we're going to take our argument, we're going to assume that the premises are true and that the conclusion is false, and then we're going to see if that leads to a contradiction, if that leads to absurdity. If it leads to absurdity, then that tells you that it's impossible for the premises to be true and the conclusion false. If it doesn't lead to absurdity, then that's going to show you that it's possible for the premises to be true and the conclusion false. What does absurdity look like in the truth tree system? Absurdity in the truth tree system is the closure of every single branch, right? So what we're actually doing is we're going to assume that the premises are true and the conclusion is false. And in order to assume the conclusion is false, what we do is we negate the conclusion, we assume that that's true, and then we do the tree. If the tree closes on every branch, then we've hit absurdity. And if we've hit absurdity, then we can conclude that our initial assumption that the premises are true and that the conclusion is false was mistaken, and thus that it's impossible for the premises to be true and the conclusion false. So we get the result that the argument is valid. If we have at least one open branch, right, so if one of these stays open rather than closing off, then that shows us that the assumption that the premises are true and the conclusion is false is not absurd, and that it's possible for that to happen, which is another way of saying that it's possible for the premises to be true and the conclusion false. Okay, so what we're doing is we're using this proof method, reductio ad absurdum, and we assume that the premises of an argument are true and the conclusion's false. And because we're working in the truth tree system where you can't represent falsity directly, in order to represent this starting point for the truth tree test for validity of an argument, what we do is we assume that the premises are true, and then we negate the conclusion and we assume that that's true. So, for instance, have a look at this. So suppose my argument is just a very simple modus ponens argument. All right? And now I want to test to see whether that argument is valid or not. Now, in order to test to see whether that argument is valid or not, what I'm going to do is I'm going to assume that it's invalid, right? And then I'm going to try and see if that leads to absurdity. So to assume that it's invalid, I need to assume that the premises are true and the conclusion's false. In order to do that, I just add a negation to that conclusion. Because what I'm doing, as soon as I situate this in a truth tree, the truth tree is saying everything here is true. So it's saying the premises are true and the negation of the conclusion is true, which is just another way of saying that the premises are true and the conclusion's false. And now I do the tree. So this is the difference between just writing down a set of propositions and then doing the tree and testing for validity. When you're testing for validity, you always negate the conclusion first and then do the tree, right? So if you sort of want a quick and dirty way of remembering exactly what we have to do here, if you've got a proposition or a set of if you've got an argument and you've got to test it for validity, the very first thing you do is you add a negation to the conclusion, and then you work through the rules for the rest of the tree. If you don't add that negation to the conclusion, you're not testing the right thing and you're not testing the argument for validity. So always add that negation. All right, now that we've added this negation, we can actually test the argument for validity. And the way we do that is we just apply the tree rules that we've learned to everything inside the tree, and then we use the completion and closure rules to tell us when to stop. So we've only actually got one proposition in here that we can apply something to, and that's this conditional at the top. So we're going to apply the rule for the conditional. The rule for the conditional, remember, is this. When the conditional is true, then either the left-hand side is false or the right-hand side is true. So we're going to branch here. And on the left-hand side, we're going to have not A. And on the right-hand side, we're going to have B. Now we look for closure. Now it's important to think of closure in the following way. Closure between a proposition and its negation on a branch is like a program that's running in the background, always checking to see if there's any closure that needs to be had, right? So it's constantly checking. Every time you write something down in the truth tree, it looks at what you've written and it goes, is a basic proposition and its negation appearing on the same branch? If so, close. If so, close. If not, then don't close. So it's constantly doing that. So you're always using the closure rule as you go throughout the tree. You don't wait till the end to close things, you close things as they happen. So if we look down this tree, we're looking to see if anything can close in order to work out whether the tree is completed or not. Look down this left-hand branch, what we see is we've got a basic proposition A and its negation, not A, and so we're going to close that left-hand branch. We look down this right-hand branch, we've got a basic proposition B and its negation, not B, and that's a contradiction, and so we're going to close that branch. Now remember what I said a moment ago about what absurdity looks like in the truth tree system. Absurdity is the closure of every branch, and that's exactly what's happened here. So what we did is we assumed that the premises are true and the conclusion's false. We did the tree and it led to absurdity. So now we can reject that initial assumption. We can reject the idea that the premises can be true with the compatible with the falsity of the conclusion, which allows us to conclude that the argument is valid. Okay? So we assumed the thing we assumed the opposite of the thing we were trying to prove. We showed that the opposite of the thing we were trying to prove leads to a crazy place, and then in virtue of it leading to a crazy place, we rejected that thing, which gets us the thing that we wanted to demonstrate. All right, that's validity. What does invalidity look like? Well, if you've got an argument, let's look at this argument. Okay, here's a slightly different argument. Now notice I haven't actually added a negation yet. The conclusion of this argument already had a negation in it. I'm going to have to add another negation to whatever's there. So that rule of thumb, always add a negation, that applies even when the conclusion already has a negation in front of it, right? So that means I'm going to add a second negation here in order to test the argument. But the basic idea is the same. We want to test the argument by assuming that the premises are true and that the conclusion is not true. And so we do that by adding that second negation, and then we do the tree. So now we've actually got two things to operate with. We've got this double negation. The rule for the double negation, remember, not, alpha. We get rid of the double negation, those cancel, and that just gets us back down to alpha. So if we've got not, B, we tick that off, we just get back to B. The next thing we have to do is the conditional. The conditional rule, remember, is if alpha, then beta, and that branches to not alpha or beta. Okay, so what we're going to do is we're going to branch this conditional. We're going to get not A on one side and B on the other side. And now we're going to look to see if anything closes, right? So that closure rule is going to kick in at this point, and we're going to try and work out whether or not the branches have to close. So we look up this branch, we've got not A, but we don't have an A, so we don't close that. We've just got the negation of the proposition, we don't have its unnegated form, and because of that we don't have absurdity, so we don't close. And similarly over here, we've just got B, we don't have not B, so again, we don't close there. So what this shows us is that this initial assumption that we made, that the premises are true and the conclusion false, doesn't lead to absurdity. And in general, what that means is that there is some possible way to make the premises true compatible with the falsity of the conclusion, which is to say that the argument is invalid. So if we come back to that analogy of trying to prove that there are infinitely many primes, suppose that you want to prove that there are infinitely many primes, and so you go, okay, well here's what I'm going to do. I'm going to assume that there's finitely many primes and show that it leads to an absurd result. So you make the assumption, you assume that there's finitely many primes, but then you don't get any absurd result. Well, that shows you that that initial assumption can't be rejected, and so you actually don't have any grounds for thinking that there's infinitely many primes. Similarly here, we made this assumption that the argument was invalid, and we wanted to see if that went to an absurd place, but it didn't. So that means we've actually got no basis for thinking that invalidity can't happen here. But that's enough to show that it's possible for the premises to be true and the conclusion false. The mere possibility, even if it's just a mere logical possibility that the premises can be true and the conclusion false, which is what we have here, is enough to show that the argument is invalid. Okay, so that's the basic idea behind how we take the truth tree system and we actually use it to use it to test the information, to test arguments to work out whether or not they're valid or invalid. Now, what we can do is we can actually use this method to come to very efficient answers to problems that would take quite a long time if we were to test them using the truth table method. So consider the following argument. This is quite a simple argument in some sense, but a kind of nasty argument to try and do inside the truth table system. You've got 1, 2, 3, 4, 5, 6, 7 basic propositions. So if you were to do this inside a truth table, the number of lines would be 2 to the power of 7, which would be quite a lot of lines to have to do, and it would be a real pain to do. If we use the truth tree method, we can get through this argument much more quickly. So let me show you how that works. So you get a sense of the gains in efficiency that we're actually buying by moving into this proof system. All right, so let's begin by writing up the entire argument. Right, so there's the argument. We've got a sequence of conditionals. We assume the start of that sequence, and then we conclude the end of that sequence. So we want to know, is this a valid argument? If we were to test it using the truth table system, we'd have this many lines to have to compute. That would be a real pain. Let's see how quickly we can do it using the truth tree method. So what we're going to do is we're just going to apply that same rule for the conditional over and over again. So I'm going to put that up here so you can see what I'm doing as I'm doing it. And I'm just going to apply that rule one after another to each of these propositions, okay? So here we go. We're going to start with A arrow B and work our way down. Now remember, I said in the previous lecture, whenever you apply a rule, you have to apply it to everything that is open, like every open branch below it. So we've got 2 open branches here as soon as we hit that B arrow C, so we're going to have to do that on the two open branches below us, so let's do that. And that rule, that closure rule, remember, is constantly trying to look for closure. Sorry, just have to get rid of that. It's constantly trying to look for closure, and notice that because we've got this A here, as soon as we wrote that not A, we got closure there, right? So that should close immediately. And now we do the B arrow C on the remaining open branch. And now we've got B here. We got not B on one side and C on the other. That B and that not B close. So that gives us a little bit more closure to deal with. And now we work our way onto the next proposition, C arrow D. We get not C, D. The C and the not C, that closure rule, constantly checking. Sees that C and that not C, it closes those off for us. And then we do the next one, D arrow E. We get not D, E. Again, that closure rule knocks out the D and the not D for us. Then we do the E arrow F, we get not E, F, the E and the not E close, and then finally we do the F arrow G, we get the not F and the G. Now, in doing this, I actually made a mistake when I started, and the mistake I made was to fail to do the thing that I emphasized that you have to do. So at the very beginning, I needed to negate that conclusion, which I failed to do, right? So when we're doing these tests for validity, we always have to assume that the conclusion is false, and if we don't do that, then we don't get the right result. So this argument is valid, as we'll see in a moment, and without that negation on that conclusion, though, we weren't going to get that result out. So we were actually going to get the wrong result. So what I've done now is I've gone back and I put that negation in onto that not G to make sure that that conclusion is negated for us. And now everything else stays the same. But I now have, if I look up the tree, I've got an F and a not F here, which closes, and the G and the not G closes. And I look at every branch, and every branch is closed, and now the tree is complete. And you can see that that wouldn't have happened if I hadn't negated that conclusion. So that's really important. That's the sense in which if you don't negate the conclusion, then you're not actually testing for the right thing. Okay, so what we did is we started with these propositions that formulate our premises. We assumed that the conclusion was false by negating the conclusion, and then we looked to see if absurdity followed. And it did, because every branch on the tree is closed. And that means that the tree is complete, because that completion rule tells us that a tree is complete when every branch closes, or when you've applied every rule that can be applied. And because of that, what we've got actually is a valid argument. It's actually impossible for the premises to be true and the conclusion false, because if we assume that the premises are true and we assume that the conclusion is false by assuming that the negation is true, then we get to absurdity, and so we reject that initial assumption, which means that we get out the result that the argument is valid. And notice that this was a lot shorter than doing 2 to the power of 7 lines inside a truth table. So this is the real gain in efficiency that you get from using this truth tree system. All right, and so that's the argument here. And so we can conclude that this argument is valid. Okay? So valid arguments are good, invalid arguments are bad, and we're trying to find the good arguments. All right. Now, consider the following alternative example. So this is exactly the same argument structurally in some sense, except that what I've done is I've reversed the position of the A and G. So whereas here I had the A as a premise and I concluded G, over here I have the G as a premise and I conclude A. So what this argument is doing is that we've got this sort of sequence of conditionals running from A all the way to G. You start at the top and then it runs down to the bottom and you get the G out. Over here what we're doing is we've got the same sequence of conditionals, but this time we start at the bottom and we run up to the top, right? So we're trying to see if you can get, we know that if you start at the top you can get to the bottom. That was a valid argument. Now we're checking to see if you start at the bottom, can you get to the top? Is that a valid argument? If we were to do this in the truth table system, it would be 2 to the power of 7 lines. That's going to be nasty to do, so let's see if we can do it in a shorter period. So again, we're going to write out the entire argument and then we're going to test it. Right? Now we start here by negating the conclusion, so we're going to do the thing that I failed to do last time properly. And we're going to apply that rule for the conditional again. It's the same rule, just put it up again for you. And we're just going to apply that rule over and over again until we're finished. So we start with the A arrow B. We're going to get not A on one side, B on the other side. Now notice that this not A and this not A, they don't close off, because in order to get closure, we need a proposition and its negation, and all we have are 2 not A's here, right? So they just stay around in the tree. Now when we're doing this B arrow C, we look down, we've actually got 2 open branches, which means that we have to do that B arrow C twice. We have to do it on every open branch below the proposition where it occurs in the tree, right? So because these 2 open branches appear below the proposition, we're going to have to do the B arrow C on both branches. So we can get not B, C, not B, C. That closure rule is still running, however, it sees this B and this not B, and it closes that branch off for us. And we tick this B arrow C off because we're done with it. Next, we're going to do the C arrow D. We look down, we've actually got 3 open branches, so that means that we have to do 3 instances of that C arrow D, 1 for each of those open branches. So let's do that quickly. Okay. Now again, that closure rule is running. It sees the C and the not C wherever that appears, and it closes those off for us. It's going to close that C and that not C for us, and it's going to close this C and this not C for us. Next, we've got the D arrow E, and we're going to do that. We look down a tree. We've now got 4 open branches, so we're going to have to do that D arrow E 4 times across each of the open branches. So it's worth noting at this point that the trade-off with the truth tree system is that although this is still going to be shorter than 2 to the power of 7 lines, you can get these expanding trees when you have a lot of conditional statements sitting inside the tree. So you've got to try and think ahead a little bit sometimes to work out, well, look, if I do this conditional first, can I get closure here? Or if I do that conditional, can I get some closure here? And you've got to try and keep the tree as small as possible. It's hard to do with this particular argument because this one just wants to keep expanding before us. But with other arguments, there are going to be sort of ways of doing it that enable you to close off some of those branches earlier than you might otherwise do, depending on the order in which you do the propositions. Anyway, because I'm just going top to bottom though, in this case, I'm just going to keep moving on to the next proposition. So the next proposition is the D arrow E, and I've got to do that 4 times across the bottom of the tree. That closure rule kicks in and looks for any closure. I've got D and not D here, so those close. I've got D and not D here, so those close. And I've got D and not D here, so those 3 branches close. Now I've got 1, 2, 3, 4, 5 open branches, and I've got 2 more propositions to do, so I'm going to have to do those 2 propositions one after the other. I'll do the first one across the 5 branches. That's going to give me some more branches to deal with, and then I'm going to get to that last proposition. Let's start with the E arrow F, do that. Okay, so now that closure rule is going to kick in again, and it's going to look at these E's and not E's, and it's going to close off those for me. So I'm going to get closure there with the E and the not E. I've got E and a not E here. I close those. I've got another E and a not E there, another E and a not E there, and the rest of it is going to stay open. Last thing I've got to do is apply this F arrow G. I've now got 1, 2, 3, 4, 5, 6 open branches down the bottom, and I'm going to have to apply that F arrow G to each of those open branches. So I'm just going to do that quickly for you, and then we're done. So we get not F, G. Okay, the closure rule operates one last time. Tick this off, and now it's looking for F's and not F's to close off. I've got an F and a not F there, so those close. I've got an F and a not F there, so those close. F and a not F there, so those close. F and a not F there, so those close. F and a not F there, so those close. And that's it. I look to see, so I've done all of these rules up in the premise set. So now I look to see if there's anything left to do in the tree. I look to see if there's any rule that needs to be applied, and I look to see if anything needs to be closed. And notice that there's nothing else that needs a rule applied. Everything that I've got left in the tree is either a proposition, a basic proposition, or a negation of a basic proposition. I can't operate on those. Those are rock bottom, so I'm done with those. And I look down the tree and I see that not every branch is closed. So I've got a bunch of open branches on the tree. And so what does that tell me about the initial assumption? The initial assumption, remember, was that I assumed that the premises are true and that the conclusion is false. And I did that by negating the conclusion. And because we didn't get absurdity, it didn't show us that every branch closed, we know that that's not an absurd supposition to make. Given that it's not an absurd supposition to make, it follows that there is some possible way to make the premises true and the conclusion false, which is just to say that we can conclude that this is an invalid argument. Now, although that was a little bit painful because we had to keep branching the tree like that, it's still more efficient than doing 2 to the power of 7 lines in a truth table, and it gives us exactly the same kind of result. We can work out that the argument is valid or invalid using the same method. Now, here's one of the guarantees about the truth tree system. The truth tree system is guaranteed to tell you that an argument that the truth table system tells you invalid is also invalid in the truth tree system, which is to say that the truth tree system and the truth table system always agree on the results that they yield. You're never going to get the truth table system tell you that an argument is valid and a truth tree tell you that the argument is invalid, or vice versa. The two systems are always going to agree. In fact, the relationship between the two systems is even tighter than that. The kind of information that you can draw out of a truth table is exactly the same kind of information that you can draw out of a tree. So remember when we were looking at the truth table system and we found we were sort of testing an argument to see whether it was valid or invalid, what we were doing was we were looking for a row in the truth table in which the premises were true and the conclusion false. If there was such a row, then the argument was invalid. If there was no such row, then the argument was valid. And then from there, what we could do is we could actually draw out a counterexample. How did we draw out that counterexample? Well, we looked at the values for the basic propositions for the row in which the premises are true and the conclusion false, and we use the values for those basic propositions to individuate that row and thereby draw out the counterexample to the argument. So for instance, if it's the case that the row in which the premises are true and the conclusion false are such that, say, A is true and B is false, then the values for A and B that I just specified, namely that A is true and B is false, those values represent the counterexample to the argument in question. That information is all stored within the truth tree. In fact, exactly the same information inside a truth table is also stored within the truth tree. And what I'm going to show you now is how to take the truth tree system, demonstrate that an argument is valid or invalid, and then draw out the same kind of counterexample. In fact, I'm going to take it a step further. I'm going to look at a case in the truth table. I'm going to look at a case for the truth tree system, and I'm going to show you that exactly the same information is being pulled out in both cases. So we'll look at the two side by side to get a feel for how they actually relate to each other. Okay, so a counterexample in the truth tree system is read off in the following way. So in the truth table system, you would read a counterexample off from a row. In the truth tree system, what we do is we read a counterexample off of an open branch. Now, the counterexample in both cases is the same kind of thing. In the truth table system, a counterexample is a value for the basic propositions in the argument. So, if you had two basic propositions, A and B in the argument, then the counterexample would specify the truth values for those basic propositions. It would say that A is true and B is false. The same kind of thing applies to the truth tree. So what we're looking for are the values for those basic propositions in order to specify the counterexample. But we don't have any rows in truth tables to read off. Instead, what we've got are branches. And in order to read a counterexample off a tree, what we do is we find one of the open branches and we actually read the counterexample off the open branch in the tree system. So here, just to remind you, is the counterexample case in the truth table system. So here you've got an invalid argument, and we can look to see that you've got a counterexample sitting inside the third row, and the counterexample itself is specified in terms of the basic proposition, the values for the basic proposition. So that's the kind of information we're going to draw out. And in fact, we're going to be able to draw out precisely the same information that we have in the truth table system in the following sense. An open branch on a truth tree represents a row in a truth table in which the premises are true and the conclusion false, right? So each of those open branches, if we were to do the truth table, each of those open branches would represent some row in the truth table in which the premises are true and the conclusion false. So this sort of information here that we're looking for in a truth table, what the truth tree enables us to do is sort of hone in, right in on that information in a really efficient way. We don't have to scan a 256-line truth table in order to find the information. We can actually take the truth tree, solve the truth tree, and then read off an open branch exactly the information that we would be looking for inside a truth table. Okay, so I'm gonna show you how to do this, but first, some important points about reading counterexamples off truth trees. The first point is that we read a counterexample off of a single branch only, which is to say that each branch specifies a counterexample, and you read the counterexample by taking the bottom of the branch and reading to the top of the tree. You don't zigzag, so you don't go up and down. You always go from the bottom to the top and from a single branch in order to get a counterexample. Second thing is that a tree may have many open branches, and when a tree has many open branches, that means that there are potentially multiple counterexamples. This is the same sort of thing that you have in the truth table system. In the truth table system, you might have many rows in which the premises are true and the conclusion false. In the truth tree system, you might have many open branches, but that's basically the same idea. You're getting potentially many cases in which the premises are true and the conclusion false. The third thing is that in a truth tree, sometimes you'll have an open branch where a basic proposition that appears in the argument won't actually take a specified value on the branch. So it won't be such that you can read a particular value for that proposition off the branch in question. And what that means is that the proposition can have either of the two truth values when you're reading up that branch. So in other words, when you don't have a proposition appear on a branch at all, but it appears in the argument, then what that's telling you is that that proposition can take any value that you want, at least with respect to the two values that you have to choose from. So you can set that proposition to being true, or you can set it to false. And what you'll see actually is that when you look at the truth table that corresponds to the truth tree, you'll have a row in the truth table where that particular proposition is true, and another row in that truth table where that particular proposition is false, and both of those rows will constitute counterexamples to the argument. Okay, so that's a little bit abstract. What I'm going to do is I'm going to make this a little bit more down to earth by getting an example, working through it, showing you how it relates to the truth tables, and then showing you how to read off a counterexample from the tree itself. Let's start with a very simple example because that's going to be easy to do the truth table with as well. So let's come to this argument again. All right, so what we do is we have a conditional, we assume the consequent, the thing on the right of the conditional, the second thing, and then we conclude the first thing, the thing on the left of the conditional. Now, what we're going to do is we're going to test to see if this argument is valid or invalid. The very first thing we do, as before, is we put a negation onto the conclusion, and then we perform the rules for the truth tree system to this argument in order to unpack the propositions that we have. We only have one proposition to unpack, and it's this top one, and we use the rule for the conditional, which gets us this. Okay, now we look to see if there's anything else we can do. Can we close any branches? No, none of the branches close. Are there any other rules that need to be applied? No, everything that can have a rule applied to it has had a rule applied to it, and so the tree is finished. Because the tree remains open, that tells you that the initial assumption wasn't absurd, namely that the premises are true and the conclusion false. So there is some possible situation where the premises are true and the conclusion false, right? So it tells us that the argument's invalid. So we can conclude that immediately. Now, if we want to read a counterexample off of the tree, we do it as follows. We pick a branch. Let's suppose that we pick this branch, and we read the values of the propositions that appear on that branch as follows. If we see that A has a negation, so if we see a not A, then we set A to being false. And if we see a proposition, like just a basic proposition without a negation, we set that proposition to being true. So because we've got not A, we set A to false, and because we've got B, we set B to being true. We can do the same thing over here. If we read up this branch, we're going to set B to being true and A to being false. Now notice that that information is really the same information. You've just got the same information appearing on two different branches in the tree. So although you can have multiple open branches, and it might be the case that those open branches represent multiple counterexamples, sometimes the open branches just represent exactly the same information, as is the case here. Okay, so this is our counterexample right here. Now, to show you that this is the same thing that we get from the truth table, I'm going to do the truth table just below the tree here. Okay, so remember when we're doing truth tables, we start by putting the matrix values for the propositions in on the left here. TF, TF, TT, FF. Then we apply our rules to each of the propositions that we have in the tree. For B and A, we just replicate those values, so those are easy. And then for A arrow B, we use the truth table rule for the arrow, which is that the arrow is true. So the arrow is false when you've got the first thing and you don't have the second thing, but it's true in all the other situations. So it's false in the second row, but true everywhere else. And we're done. So that's the truth table for the argument, and this is the truth tree for the argument. And now, the truth table for the argument, we're looking for a row in which the premises are true and the conclusion false. We read down the table, and we can see that in the third row, oops, put that up again. So in the third row, we can see that we've got a counterexample to the argument in the truth table. And remember the counterexample that we drew out of the truth tree, the counterexample that we drew out of the truth tree was that A is false and that B is true. And we look at the values for A and B in this third row for the truth table, and it's exactly the same information. All right? So by doing the truth tree, we're able to pull out that row of the truth table just by reading off the open branch in the truth tree. And that's in general what you do with the truth trees. When you complete the truth tree and you've got, for an argument that is, and you've got an open branch, you could just read up that open branch and read off the counterexample to the argument, which enables you to find that row in the truth table that makes the argument invalid and just hone in on it really specifically and in a really quick way. Okay, as I said, though we've got to be a little bit careful. We have to read off from a single branch only. We have potentially many counterexamples to read off from a single tree, and sometimes a basic proposition won't have a defined value. So although the first and the second point here I think are pretty straightforward, this third point is a little bit unclear, so I'm going to show you what that third point looks like by considering a particular case. So consider the following argument. So this is really just a variation on the case that I just gave you, except in this case what we're going to do is we're going to have two different conditionals that we have to solve. So we start by negating the conclusion again. We then operate on these conditionals using the rule for the conditional from the truth tree system. And the rule for the conditional just tells us to branch each of these conditionals to unpack them, with the thing on the left being false and the thing on the right being true. So we start with the A arrow B, we branch that, we get not A, B, like that, and then we do the second branch, and on that branch we get not B, C, not B, C, like that. Okay, so what we can see here is that we've got the sort of the similar sort of situation where we can close whatever we need to close using the closure rule, but we can only close that one branch, and then everything else is going to stay open at this point. Now, let's suppose that we have another proposition inside the tree, and that other proposition is going to be different to the propositions that we've got up so far. Rather than being one of these conditional propositions, the proposition is just going to be something like this, either D or E. So I'm just going to add that into my premise set. So that's a new premise that I've just added to the argument. And now I'm going to perform the disjunction D or E at the bottom of the tree applied to every branch. So I'm going to do it here. I'm going to get D or E. Now notice that the argument stays invalid. Like adding that proposition didn't make the argument valid, adding that premise. So it's interesting for you to think about when you've got an invalid argument, what you might add to the premises to make the argument valid. But for now, I just want to focus on the fact that the argument's invalid, and we've got a bunch of open branches down here. Now, when we look at these open branches, we can start to draw out counterexamples from those open branches in the way that we've been drawing out the counterexample from the previous tree. But what I want to do is highlight the difference between two different branches. So down here, I'm going to call that branch 1, and over here, I'm going to call this branch 2. And I want to look at these two branches separately. So on branch 1, I'm going to read the counterexample off as follows. I read up the branch and I look at the propositions that I've got in that branch, the basic propositions and their negations, and I set the values of those propositions as I read up the branch. So I look up the branch, I've got D, and remember when you've just got a proposition on its own, you set it to being true. I've got C, true. I've got B, true. I've got A, false, and that's it. That's all the information. I've got C then again. I've got C appearing twice, but that doesn't mean anything. It doesn't add anything to the counterexample. The counterexample is the same. So that's just the first counterexample. And now the second counterexample, which I've called 2, is reading off this right-hand branch upwards. What we've got here is we've got E equals T. So we've got E is true. We've got C is true. We've got B is true. And we've got A is false. Now the big difference between these two counterexamples is that for this first counterexample, I've got a value for D, but I don't have a value for E because E does not appear on that branch. And for this second counterexample, I've got a value for E, but I don't have a value for D because D doesn't appear on that branch. Now a counterexample, when you're reading a counterexample off an open branch in the tree, it has to set a value for every proposition that appears in the argument. Because both D and E are propositions that appear in the argument, and by that I mean basic propositions that appear in the argument, the counterexample really actually has to specify a value for those. Given that they don't appear on the branch though, it's not obvious what value to give those two propositions. Actually, what we do here is we take each of these counterexamples and we set the value for E or D respectively to whatever we want. So if we take this first counterexample, what we can do is we can just take this first counterexample, we can add E in and we can set it to T. Or we can take this second counterexample and we can add D in and we can set it to F. But similarly, we can also take this first counterexample and set E to F, or we could take this second counterexample and we can set D to F. Like we don't have to set the propositions to any particular value. Another way of putting the point here is that each of these branches, these open branches, is really hiding two distinct counterexamples. On the first branch, the one that I've labelled 1, where we've got D but no E, that is actually telling us that E does appear here, we just don't know what the value is, so you can set it to whatever you want. Similarly, over here where the 2 is, where we don't have the D, D does appear there, it's just that we don't have a value for it, so we can set it to whatever we want. So this first counterexample is actually hiding two counterexamples in it. So if we take this first counterexample, what we get is sort of counterexample 1.1, and that counterexample 1.1 has that D is T, C is T, B is T, A is F, and there's some value for E. We're just going to set it to T. But that one open branch also houses a second counterexample where E takes the other value. So if we have counterexample 1.2, what we're going to have is we're going to have D equals T, C equals T, B equals T, A equals F, and E equals F. And if we went and did the truth table for this argument, what we would see is that both of those rows are rows in which the premises are true and the conclusion's false. Right? So that what we had here where we didn't get a value for E, E can take either value, and when you look at the truth table is going to have both counterexamples in it. So in other words, when you have this situation where you don't have a specified value for a proposition on a branch, it doesn't mean that the proposition doesn't have a value. It means that there's a counterexample either way, where the proposition takes one value or it takes the other. So what I said for counterexample 1 here goes for counterexample 2. There's going to be two counterexamples there where D takes a value either way. So there's going to be one counterexample where all of the values for A, B, C, and E are the same, but D is T, and then another counterexample where A, B, C, E have the same values as they do here, but D is F. And if you look at the truth table, both of those counterexamples, both of those rows are going to be rows in which the premises are true and the conclusion false. So actually, where we've got two open branches here, we've got hidden in those two open branches information about 4 distinct counterexamples and 4 rows in the truth table under which the argument fails. Okay, so that's what I mean by this third thing. So you've got to be really careful when you're reading counterexamples off open branches in trees to make sure that you don't ignore the values for some of the propositions that you have in your argument. Every proposition, every basic proposition, which is, say, every propositional letter that appears inside your argument, inside your premise set or your conclusion, must take a value in a counterexample. And when you don't find that proposition appearing on a branch, when it just doesn't seem to take a value, all that means is that it could have either value, but you have to set it to some value when you actually offer a counterexample to an argument. Okay, and that brings us to the end of propositional logic. So what we've done is we've taken a very basic language that enables us to translate out English arguments into a sort of formal system. We've then offered a syntax and a semantics for that language, and then we've built the semantics into a first proof system, which enabled us to test for validity. And then we've built that, taken that a step further and developed a second proof system, which does everything that the first proof system could do, except in a more efficient and more straightforward manner. What we're going to do next is we're going to dial up the expressive power of the language. So far the language is very simple. There are very few things, in fact, that you can say, and a lot of the structure of English isn't getting transferred into the propositional language that we've been looking at. Now, for the most part, that's not a problem. Sometimes you want to ignore a lot of the structure in English when you're actually building a logical language, because you want to focus in on the logical structure and ignore a lot of the other stuff that might be occurring in the language. But it turns out that there's structure in the English that we're blind to at the moment with the language, the propositional logic that we've been using, that is really important for working out the validity or invalidity of an argument. So what I'll do in the next session is I'll look at some arguments that we can't handle using the propositional logic we've got so far, and then we'll consider how we might develop that language so that we can actually handle those arguments. And this will take us into the second part of the course, where we look at the language monadic predicate logic. A monadic predicate logic is a more complicated language that enables us to prove the validity and invalidity of a greater range of arguments that we might be interested in. Okay, until then, good luck, and I hope that you spend a bit of time working through some of these truth trees. The bottom line is that in order to get proficient with the truth tree system, you've got to do a lot of examples. So just sit there, work through a lot of cases, and see how you go. All right, thank you.